That's regarding transition metals. So starting with the first one, aqueous copper 2 salts contain blue colored complexes, right? And you're being asked to identify. So you're being asked aqueous copper 2, they contain blue colored copper ions. Give the following information for each of these reactions. You have to give the ionic equation with concentrated hydrochloric acid and the type of reaction, also the color and the state of the. So first thing, remember this, that there's going to be questions regarding ligand exchange, and
Yes,
especially
I haven't forgotten them.
especially with copper ions, and you have to just remember these. So for example, if you have copper with water, that's copper with 6 water molecules. Copper is +2, water is neutral, so the overall charge would be +2, right? You do know what a complex is, right? This thing.
Yes.
This is a blue colored complex. This is copper H2O6, right? I mean, that's given away H2O6 2 plus. If you add ammonia to it, ligands will get exchanged. Ammonia molecules are going to come in and they're going to knock out the water molecules. And they could knock out any number of NH3 molecules, sorry, water molecules. Like all 6 of the water molecules can be knocked out. Then it would be copper with NH3 6 NH3s. Or what can happen is, just a second, my mouse has stopped working. Or it could be, just hold on a second. Can you hear me?
Yes, sir.
So for some reason my laptop is stuck. On my, just 1 second. Can you hear me? Okay, so it's working now. So you could have NH3s, and the NH3s will get, so it could be all 6 NH3s, right? So you could have either 6 NH3s, or you could have 4 NH3s, or you could have 3 NH3s and 3 water molecules. So anyways, it's still the same complex, and it's going to be blue, dark blue in color. Is that clear?
Yes.
And similarly, you could have HCl as a HCl, concentrated HCl as Cl-1 as a ligand. So the copper will get surrounded by Cl ions. Now, Cl ions are bigger in size. So only 4 of them actually manage to, I mean, you run out of space. Like Cl is a bigger ligand. So it forms a CuCl4 2-, which is a complex, and it's got a greenish yellow color. Is that clear? Is this clear?
Yes, sir.
And then you have NaOH. This is going to be a precipitation reaction. What will happen is that 2 of the water molecules are going to get knocked out, and they're going to be replaced by OH ions. And usually it's just 2. And the reason for that is that after 2 OH ions have replaced two of the water molecules, the molecule becomes neutral. So it doesn't really attract any more OH ions. Previously this was copper. The complex had a positive charge, but once 2 OH ions they replace it, the positive charge goes away. So further OH ions are not going to get attracted to it. So usually it's just 2 OH ions. So this is copper hydroxide, which is a insoluble pale blue precipitate. So you have to remember all of this. You have to remember the complexes that are formed. And the same is true for cobalt complexes. The same thing happens. Cobalt with 6 water molecules, that's pink. Cobalt with water. If you add OH ion, you get a green precipitate. If you add NH3, you get a brown solution. And this one is, forget this. If it's COCl4 2-, then it's going to be a blue solution. So they're exactly the same complexes for cobalt, but the colors are going to be different. So if I go back to the question, this one, he's seeing the reaction with sodium hydroxide. So ionic equation would be that it's copper with how many? 6 water molecules, right? And it's +2. So if you add OH ions, then what will happen is that the 2 of the water molecules are going to get knocked out. And it's going to 2 water molecules get knocked out. That is what's going to happen. It's a precipitation reaction. And the color is a pale blue precipitate. Is this clear?
Yes. Will it always, will two water molecules always get knocked out or something? Or
Yes. In this case, it's always 2. And then I told you the reason, like once the 2 OH ions, they replace this becomes neutral, right? Because it's copper +2. So a neutral molecule is not going to attract other OH ions. Yeah, positive ion will attract OH ions, but a neutral one will not. So usually it's just 2. What happens with hydrochloric acid? It's going to be the same thing, except now it's going to be with Cl ions, 4 Cl ions, and what will happen is that it would become CuCl4 2 minus, and all 6 water molecules get knocked out because they're using concentrated HCl, so there's a lot of Cl ions. The type of reaction, this one is ligand exchange. And the color is it's greenish yellow. So is this clear that they always ask you the same 2-3 things? It's always the same. It's either cobalt exchange, ligand exchange, or copper ligand exchange. And they're exactly kind of the same. Is that clear?
yes.
Plus, you also got to remember the equations of these ligand exchange reactions. So the equations are given below. You have to remember all of this. Now, this one is I mean, we can kind of skip this one. It's a moles question, so we can skip that. The next one is he's asking you to write the electron, 29 electrons. So it's 1s2, 2s2, 2p6. Then you have 3s2 and 3p6. And electrons goes into the 4s and then the 3d. But in case of copper, it's 3d10 and 4s1. Because copper was the special case with 29 electrons, but it's copper 2 ions. So that means this has gone 1 electron and this is gone, it's going to have 9 electrons. Is that clear?
Yes.
And state the color of the solution. So it's the same thing. This one is blue, this one is greenish yellow. And the other very typical question they're going to ask you is about colors. Why are they colored? So the answer to that is
The VD transition.
yes. So Rajni, maybe my laptop might shut down, TK. So I'll be back on. I'll be back online just if it shuts down. Although it is, let me just. Not sure what's happening. It's still on charging, but it's not getting charged actually. Just a second. I think it's now getting charged. So hopefully it's fine now. I said this one. So the colors of complexes now. So the colors are, I mean, the PDF shapes of complex is this part, right? So this has all to do with colors. So I'll explain this very quickly. Why are they colored, right? What's the reason why are they colored? Do you know why they're colored?
Because of DD transition.
Because of?
Um, because of DD transition.
Exactly. The thing is that that you have a d subshell, and d subshell has 5 orbitals, and some of the electron densities lie between the axis, some of them they lie on the axis, right? Like the green ones. So think of this, and the d subshell is inside the atom. It's not on the outside. The outer shell is different. It's inside the atom. So what happens is that every transition metal has a bunch of electrons in the d subshell, and the electrons are distributed in the d subshell. So there are all sorts of 5d orbitals, electron density between the axis, on the axis. The d subshells are considered degenerate, which means that they all have the same energy levels, right? But when they form complexes, what happens is when these water molecules come in, this copper ion has a positive charge, and the water molecules, they get attracted to the copper ion. The lone pairs on the ligand comes very close to this green orbital over here. So it kind of becomes harder to keep electrons in the green orbitals and kind of becomes easier to keep electrons in the pink ones. Is that clear?
So can you please repeat it?
I mean, imagine a copper ion, right? A copper ion inside, it's got lots of subshells that are inside it, right? So,
Yes.
so the thing is, the 3D subshell is also inside the copper ion. Remember, the ligand has nothing. Think of this as the shell of the copper ion, right? These orbitals are inside it. They're protected by it. The water molecules are sticking on the outside, right? So, so what's happening is the d subshells are degenerate, which means they have the same energy level. They're all identical. Is that clear?
Yes.
Just like the px, py, and pz, they're all identical, except that the orientation is different, right? So the d subshell is exactly the same. All the orbitals are exactly the same, except the orientation is different. So the electrons are distributed in the d subshell. The d subshell has there are two types of d subshells, orbitals. They have electrons. I mean, this is what a d orbital looks like, right? It's so the d subshell is this one. So the electron density would probably be uh, between the axis. Sometimes it's going to be on the axis. So you must know that if it's in the dyz orbital, dxd, dxy orbital, the electron density would be between the axis. And if it's in the dx square minus y square or dz square orbital, the electron density would be lying on the axis. Is that clear? So, so simplistic model looks like this. This is all the d orbitals. The electrons could either be in the pink ones that are lying between the axes, and they could either be in the green orbitals which are lying on the axis, right? So the electrons would be filling up the d orbitals, and they would be filling this space over here. Is that clear?
Yes.
Now, due to the presence of ligands, the d subshell splits into two energy levels. What happens is that when the water molecules come in, remember the water molecules have nothing to do with the d subshell. They're just getting attracted by the copper ion overall, right? Because the copper ion overall has a +2 charge. So the water molecule and its lone pairs are getting attracted to the copper ion because overall it's got a +2 charge. So the lone pairs are attacking the copper ion on the axis. So if there's a lone pair here and you've got your d electrons over here, then it would be harder to keep electrons in this green orbital over here. Is that clear?
Yes.
And it would be a lot easier to keep electrons in the pink orbitals over here because they're not on the axis, right? So what happens is that the d orbitals which were identical are now no longer identical because now there's a difference between the green and the pink ones. The pink ones are going to face less repulsion, and the green ones are facing a lot more repulsion. Is that clear as well?
Yes.
So what's going on now is that the d subshell is the ones on the axis are at a higher energy. Dx square minus y square, dz square, these ones, which I showed you in the picture over here. Dz square and dx square minus y square, they are at a much higher energy level. And the other ones were the pink ones, the ones that were between the axes. Dx, dyz, dxc, dxy. They are between the axes and they have a lower energy level because it's easier to keep electrons there. So the d subshell has split into two energy levels. And the electrons can sort of jump in between. They can have this transition. They can move from the pink ones to the green ones. But if they move to the green ones, they have to face a lot of repulsion, which is why they must be very energetic as well. Is that clear?
Yes.
So the electrons would be jumping around. Basically, they'll be jumping. The transition would be happening between the axes, on the axis. So the electron, if it switches, it needs more energy to be on the axis. If it goes to the pink ones, there it should have lesser energy because it's not facing a lot of repulsion. So the electron could jump around. And the d subshell must be incompletely filled. I mean, this was one condition for transition metals, that the d subshell, it must have an incomplete d subshell so that the electrons can move around. Otherwise, if it's full, then the electrons will not be able to move around. So it absorbs an energy that belongs to the visible spectrum. Energies are proportional to frequencies. So it absorbs a very specific frequency that matches frequencies from the visible spectrum, which is why you see a complementary color. That if you see a color missing, so you're going to see a complementary color. That means if something absorbs red light, then that is the only frequency that you're not going to see. You're going to see all the other ones, but you're not going to see red light. So that means you'll see something that is bluish in color. Is that clear?
Yes.
So and this is the explanation for, I mean, this PDF is getting stuck. Just a second. Let me just. So you're going to get two questions on this. Just hold on 1 second. Let me. So anyways, you're going to get two questions. First one, why are they colored? Due to repulsion from lone pairs on ligands, ion on ligand. In metal complex, the d subshell splits into two energy levels. Electrons from the lower energy d orbital gains energy and moves to the higher energy d orbital. The energy gap delta E matches frequencies which are part of the visible spectrum. Since E is equal to HF, hence a complementary color is seen. That's the first explanation. The second one is, why does the change of ligands changes colors? And the answer to that one is that if you have different ligands, they're going to have a different lone pair. I mean, no two lone pairs are exactly the same. The lone pairs on water molecules and the lone pair on NH3 are going to be different. They would have a different charge density. So different ligands exert a different amount of repulsion, which creates a different energy gap as the d subshell splits. Since E is equal to HF, a different frequency is absorbed from the visible spectrum. And when electron moves from a lower energy d subshell to a high energy d subshell, which is why a different complementary color is going to be seen and a different color is going to be seen. So that is the other question that they're going to ask you. So he's saying, why do they have different colors? And it's just a 2-mark question. So first one is different ligands, right? Specifically their lone pairs will exert a different repulsion on D subshell. So when the D subshell splits, a different energy gap delta E would be created between the delta E would be created So when electrons move from low energy d orbitals to high energy d orbitals, a different frequency would be absorbed since E is equal to HF. So you're going to write that. Is that clear?
Yes.
So you can complete that. If electrons move from low energy d orbital to high energy d orbital, a different frequency from the visible spectrum is absorbed since E is equal to HF. So that is what you're going to write. I'm going to quickly just like the shortest possible mark scheme answer. Just a second. Where's the? It's 9701 S19 QP42. Just a second. 9 S. Not this. They just gave 2 marks, not the. I mean, because it was just a very short 2 mark. I mean, it could have been a 4 mark question as well. So energy cap is different. For and different frequency wavelength of light absorbed, transmitted, or reflected. Okay, those were the 2 marks. Is that clear?
The energy gap is different because of the lone pairs, right?
Yeah, because if you have a different ligand, a different repulsion would be like if I go back.
Repulsion.
So a different amount of which creates a different energy gap on the d as the d subshell splits, right? And since E is equal to HF, a different frequency is absorbed from the visible spectrum when electron moves from low energy d subshell to a high energy d subshell. Is that clear?
Yes.
So then the next one is so let's go back to the question. So copper 1 and silver 1 salts are colorless. Why is that? Now in the case of copper 1, the D is completely full. Like if you write the whole electronic configuration, it comes out to be, I mean, it was 3D10 and 4s1, right? But copper, so the D is full. So the first thing is you're going to talk about D being completely full. And if it's full, then no transition can happen. Is that clear as well?
Yes. And the same is applicable for silver 1 salts as well.
Exactly.
Thank you.
And D subshell is full, complete, and no electrons can be promoted. So you can't do that. So that's the answer. Now the next one is, this one is about casestability. Casestability is simply an equilibrium constant. Or you can say it's the Kc of equilibrium of ligand exchange. So you think calculate the solubility, and this is solubility. So let's ignore that. He's saying use Lee-Chatterley principle as applied to equilibrium 1 and 2 to suggest why AgBr dissolves in concentrated NH3. So why does it dissolve in concentrated NH3 AgBr? The reason is, if you have concentrated NH3, right, where would this equilibrium shift? Forward or backwards?
Backward.
If you have,
No, forward. Yeah, yeah. Forward.
so it's going to
Maybe
shift.
forward because there are more moles to the left.
Okay, so it's going to shift in the forward direction. But more importantly, the casestability value is kind of really high. What does that mean? Do you get more products anyways? Like where is the equilibrium? Which side does the equilibrium favor based on the casestability value? What is the casestability value? That's simply the Kc for a ligand exchange reaction. It's product concentration divided by the reactant concentration, right?
Yes.
I mean, casestability is simply Kc. It's simply equilibrium constant for a ligand exchange reaction. So will you? So by just looking at the casestability value, will you have more products or more reactants?
More products.
So that means it's going to favor the forward reaction anyways because it's got a very high casestability value. So even if you add a little NH3, the reaction will still favor the, I mean, it will still favor the formation of products, right? Is that clear?
Yes.
So what's going to happen is that that the silver ions will form this complex So the concentration of silver ions will decrease, right, in the solution. And if the concentration of silver ions decreases, the top reaction also shifts in the forward direction, even though it has a small Kc value. I mean, it's just 5 into 10 to the minus 13. But as the silver ion concentration, as the silver ions, they decrease in solution. Why are they decreasing? Because all of them are combining with NH3. So as they
Yes.
decrease, the equilibrium in the first one, the dissolving part, this is the dissolving part where the AgBr dissolves. It will start moving in the forward direction. So this is how you're going to explain using Lee-Sharpe principle. Is that clear?
Yes.
Then again, this is what is meant by the term monodentate ligand, one that can form only one dative bond with a metal ion, just one. It might have more than one lone pairs, but it can form only one dative bond. Similarly, you have bidentate ligands and polydentate ligands that are capable of forming many dative bonds. Like, just wait. The PDF is stuck again. So you can, sorry. So you can have so this one is exactly the same. Copper sulfate aqueous, a few drops of NH3, observation and formation of the complex ion. And I would want to let me open the PDF. This is again ligand exchange. So this one, again, ligand exchange, and so this is like this is an example of a polydentate ligand. You've got a metal ion, and it's surrounded by all sides by a single molecule. But different parts of that single molecule are forming dative bonds, like the N lone pairs, the oxygen over here, the oxygen over here, the oxygen lone pairs over here. So different parts of the same molecule are forming a dative bond with the metal ion. So that's an example of a polydentate ligand. This is an example of a bidentate ligand. That you have one molecule, but it's capable of forming two dative bonds. Like one part of the molecule forms a dative bond from this side, the other part of the molecule forms a dative bond from the other side. Is that clear as well?
Yes.
And you have, so this is what I was talking about, the ligand exchange reaction equations. So when you add a few drops of NOH, what happens? A few drops of NOH, OH ions come in, the copper water molecules, they get replaced, copper hydroxide is formed, and it's a pale blue precipitate, and it's insoluble in excess. When you add a few drops of NH3, again a pale blue precipitate forms. What happens is that initially, right at the beginning, NH3 acts as a base initially. NH3, instead of reacting with the complex, instead of replacing the water molecules, what it does is it instead reacts with the water molecules, ends up forming NH4 plus 1 and OH ions. The OH ions then come in and they knock out the water molecules and they form a pale blue precipitate of copper hydroxide. But when you add NH3 in excess, in large excess, what happens now is, now you've got a lot of NH3. Those NH3, then they come in and they start knocking out whatever ligands are attached to it, and they start replacing them, and NH3, the copper then ends up forming a complex with NH3. So remember this thing for NH3, that it's not going to, the ligand is not going to be NH3 all of a sudden. What will happen is that initially the OH ions would come in, and then those OH ions will get knocked out by NH3. Is that clear?
Yes.
And if you add NH3 in excess right from the beginning, then the copper with 6 water molecules will directly turn into copper with ligands getting replaced by NH3. And that's a deep blue solution. So he is asking in the question, so in the question, he's been asking about, where's the question? So let me, so in the question, a few drops of NH3, observation. You're going to get a pale blue precipitate. So this one would be a pale blue precipitate. And the formula would be copper and hydroxide, and you can either add water molecule next to it. Right? And excess of NH3, you get a deep blue solution.
Deep blue.
So either all 6 would be, I mean, you can write all 6, or you might add in a few more water molecules into this, like 4 NH3s and 2 water molecules. If you add excess of NaOH, you again get a pale blue precipitate. And this time you again form a copper hydroxide. When you add Cl ions, it's going to become CuCl4, 2 minus, and this is going to be your greenish yellow solution, right? Is that clear?
Yes.
So remember, it's the same ligand exchange. I'll share the notes with you, but it's the same ligand exchange, and you must know what the equations are. And this one over here, I think when water is added to concentrated cobalt 2 chloride, the color of the solution changes from blue to pink. Explain this observation. No equation is needed, but you should include reference to electron movement between orbitals in your answer. So basically, the ligand is getting changed. So it's the first, I mean, you had cobalt with 4 Cl ions. This was your, I mean, this is your, so I'll use the board here. So where's the, so this one. So cobalt with Cl ions, that's a blue solution. Cobalt with Cl ions, that's a blue solution. Cobalt with water, that's a pink solution. So this is the part we're dealing with. So cobalt, CuCl4, that's this one is blue. And you're seeing it turned into, if you add water to it, so there would be 6 water molecules that would be attached to it. Two plus, and this is going to be your pink. So the question is, why is the color changing from blue to pink? So it's that answer that we did earlier, that if you add a ligand, a different ligand lone pair will exert a different repulsion on the D subshell.
Okay.
And the D subshell will split into 2 sets of orbitals, and it's going to have a different energy gap, delta E. An electron would move from the lower energy to the higher energy, and it's going to absorb a different frequency from the visible spectrum, which is why a different complementary color would be seen. It's the same answer. Is that clear?
Yes.
And I mean, this is electrochemistry. This one is casestability. You just write products over reactants. That's it. That's the expression. It's the same ligand exchange. Cl ions coming in. So,
I'm fine with the stability.
huh?
The stability constants, it's fine. I can do it.
Okay. What is meant by a transition element? So it's any element that has an incomplete, it forms an ion, a stable ion that has incomplete D subshells. Because remember, for transition to happen, the D subshell has to be incomplete for the electrons to, I mean, for the electrons to move around within the D subshell has to have some space available, right? Is that clear?
Yes, sir.
So this one is, this is electrochemistry, forget that. What is meant by the coordination number of 6? So that it means that the metal ion forms 6 dative bonds. codative covalent bonds or coordinate bonds. State the formula of X including its charge. So he's saying there's Ru forms complex ion, and one such complex ion X, the ruthenium ion, has a coordination number of 6. First thing, there would be 6 dative bonds that would be formed. Each complex ion has one Ru2 plus ion, one Cl minus 1 ion. So there's one Cl minus 1, right? One SO2 molecule, and the remaining ligands are NH3. So how many NH3s would there be? If it's got a coordination number of 6.
2,
Raj,
right?
it's going to be 4. Like you need 6 of them. I mean, you need. He said that
It's
the
one Ru, one Cl, and one SO2.
are you
Yeah, totally 4. Yes.
is the middle one, right?
Yes.
So the ones that are coming or attaching it from all sides, there would be 6 of them. He said one Cl, one SO2, and this the rest 4 NH3s, right? So and Ru is 2 plus. So what is the charge on this? Now you don't write the charge individual charges, but to calculate the overall charge, this is 1 minus NH3 is neutral. So what's the overall charge? I think it's 1 plus, right?
Yes.
So so you don't write the individual charges, you write the overall charge. The next one is he's saying that draw the 2 isomeric forms of X in the boxes below. Your diagram should show the 3-dimensional shapes of the 2 isomers, how each ligand is attached to the central. I mean, this is your. I mean, think of this as coming out of the page. This one as well, and that's your z-axis. So 6. So 6 sides. Now, so he said 4 NH3s, right? So the 4 NH3s could be in this order. And the Cl and the SO2 could be over here, right? And the whole thing would have a charge of, it will have a charge of +1. That's one. The other arrangement could be that the Cl and SO2 are right next to each other. I mean, they would be 90 degrees apart, and this would be NH3s, right? Is that clear?
Yes.
So those are the 2 isomeric form. Draw 2 isomeric form, how each ligand is attached. So just the type of isomerism. That's a geometric. So that's a geometric isomer, right? Is that clear?
Yes.
And and remember there are 2 types of isomerism. Like if we go over here, there's cis trans and geometric isomers, which is that groups could be together or groups could be opposite to each other, right? You can have that in like if you have 2 ligands of one type, then they would be opposite to each other, or they could be right next to each other. That could also work in if you have 3 ligands, then 2 of them could be like opposite to each other, or all 3 of them could be 90 degrees apart, right? And you can also have that in bidentate ligands, like 2 ligands could be opposite to each other and 2 ligands could be right next to each other. And then you would also have optical isomers, which is that that mirror images. Mirror images will happen in the case of bidentate ligands. There could be 2 molecules that are exact mirror images of each other, but they are non-superimposable, just like your 2 hands. They would be just reflected versions of each other in octahedral complexes with coordination number 6. So, but that would need bidentate ligands, at least either 3 bidentate ligands or 2 bidentate ligands arranged in this order with the 2 Cls right next to each other. Is that clear?
Yes.
Now the next thing is, what's the other one? Explain the origin of the color. So the whole thing, you have to write the whole story. Ligand lone pairs, they cause repulsion, these substance splits into 2 energy level electron, and an energy gap is created. Electron gains energy, absorbs frequencies from the visible spectrum, and moves from lower energy to higher energy. And when a frequency from the visible spectrum is absorbed, a complementary color is then seen. Right? Is that clear?
Yes, sir.
So transition metal, origin of the colors, it's the same question. And state the shape, this is going to be octahedral, 6 bonds. Write the equation for the reaction with an excess of CN9. So they've given you everything. It's like 6 water molecules replaced by 6 CN9s. You can write the equation, right?
Yes, I can.
Define the term monodentate and complete the diagram to show the 3-dimensional shape of. So one of them is NO. So one of them is NO. So the rest would be CN, right? And then you have explained why the color of the 2 complexes are different. Again, different ligands. So you write the whole story again, right? Define the term coordination number, the number of data bonds, coordinate bonds that are formed between a metal ion and a ligand. This one is about isomerism, right? So what's the trans isomer? The cis isomer is the Cls together, right? The trans isomer would be that the Cls would be
They will be
opposite.
in the opposite side.
Yeah,
Yeah.
and the OX, whatever OX is. And then there's going to be an optical isomer, right? The optical isomer would be a mirrored version of this thing. Right? Is this clear?
Yes.
So just reflected in exactly the same order. This one is about polydentate ligand. So it's a molecule, a ligand that is capable of forming many dative bonds with a central metal cation. So write an expression for casestability. You can do that. And this is mostly about casestability. This one is again about the same thing. So most of the questions are like really typical questions there. They're exactly this, the type of stereoisomerism over here. So you can, the 3 Cls and 3 NH3s. Just show the 2 isomers. So either the 3 Cls could be, I mean, this is the example, this one, where you have groups of 3. So either the 3 of them would be 90 degrees to each other, or 3 of them, 2 of them at least would be 180 degrees apart. Is that clear?
Yes.
So what suggests why one molecule of X forms 4 dative bonds, because it's got 4 lone pairs. That's it. It's got 4 NH2 groups and it's got 4 lone pairs, right? And you can construct the equation for this. He's saying this thing reacts with cobalt 2 ions to form a new complex. Now, to form a new complex, right? It's this thing. So how many dative bonds can it form? It can form 4, right?
Yes.
So how many water molecules can it replace? Like water molecule,
4
4.
water molecules.
So the new complex would be, I mean, the product that would be formed would be, they would, I mean, 6 C6H18 N4 is going to come in, and only 2 water molecules are going to be left because 4 will be replaced. That's going to be your product, right? Is that clear?
Yes, it is.
So Raji, any other questions about, I mean, this one he's talking about, and also remember, in an octahedral complex, the ligands that are on the axis, this one, and I think it's this one that's on the axis, they're going to face more repulsion. So they're going to be at a higher energy level. The other ones that are between the axes are going to be at a lower energy level. Is that clear as well?
Yes, sir.
And this is exactly the same. Copper ions, a few drops of NH3, excess NH3. So you just keep writing that. Okay. So any other questions about this? I'll share the notes with you. Or maybe, I mean,
This was only where I was facing problem, the substitution of like ligands and
I'll,
um yeah, the colors and all. I wasn't able to do past paper
so
questions based on that.
remember,
So
it's
now I guess it's fine.
so basically it's exactly the same. This parts. Just remember or memorize this section. I don't know why everything is hanging. So the board has hung up. Just a second. It's still not working. So I'll share the link of the board. Make sure you go through this. There's one part where the board is stuck. So there's one part where the whole ligand exchange and the colors, etc., everything are discussed. Right? Is that clear?
Yes.
So I'm sending you the link of the board. Just don't open it on your phone. You can make sure open it on a bigger screen. Okay. So send me any questions if you have any, TK, later as well. Okay, Rajni. Take care.
Yes, sir. Thank you.